Okay, right.
There's some bar there where you.
Hi, Matthew. Can you hear us?
Yep, can hear.
Cool.
It's all good.
Okay, thanks. Good.
It's a bit in the dark.
Sorry. Almost scared me.
That's because it's breakfast time in Japan. Or is it lunch?
No, it's dinner time now.
No, it's 10 p.m. here,
Early.
Hi.
so a little late.
I think it's more a function of where your lighting is than of it being late.
I was going to say, it does look very bright there. Through the window, not just the ceiling.
No, I think it's pretty dark outside.
Yeah, it's dark outside. That's not outside.
It's
Kitchen
the
is
night
very-
out of the kitchen.
Yeah. It is quite a small apartment. It's not a large one.
You're in Japan now. Land of small apartments.
At least we can share this.
Yeah, just looking for the sharing option.
Okay.
But maybe you even have a bedroom, why don't you? Or is this it?
Or just screen.
Yeah, that should work as well.
I had my booster shots at the weekend. I now have.
Okay.
You want to make it?
Yeah, so Matthew, you are recording the session, right?
I can do. Have you not managed to figure out how to record from? It says pause recording, so it's already recording. Someone has already said it recording, but it wasn't me. So
Okay, interesting. Yeah, I think there was a symbol there, so I was just checking. But yeah, so recording would be useful. So yeah, I'll probably start in a minute or so.
I even go to text to see what I'm doing to show that. Actually, not.
I think you can start wherever we're ready.
Okay, good.
Well, no.
Okay, so can you get it full screen? It's not quite, it matches.
Is it local here or?
Oh, okay.
Yeah, it's local file.
So we can open with. No. Open with Adobe.
Yeah, well, let's do that. How was that therapy day? The meeting with therapy basically. Yeah. We have made it. If it was for buses, got this little randomly decided not to come. Well, I was 3 minutes late for my actually was trying yes, I was able to.
Okay, so just checking everyone online, can you see the slide? It should be a full screen slide with black sidebars. Hello?
Yep. Yes.
Okay, okay, that's great. Okay.
When you have one message in the chat,
I'll check the.
okay.
Okay, if you could keep track of the chat, that would be good.
Hans-Wolfgang and focus on it.
Okay, yeah. So welcome everyone to the seminar talk today. And I'll be talking about improving GHC Haskell profiling, which is some work that we did jointly together with Phil Trinder in Glasgow, and a lot of his work was done by one final year student, Rory McGregor, in terms of implementation and measuring the system. So before I get started, one part of my thinking of giving the talk now and at this point is to introduce a bit of a systems topic into the series of live DSG seminars. Because I think in one sense, we as a group are a bit like micro SPLI in the sense that we have programming languages bringing together the topic area of people different topic areas about formal methods with programming languages. And that's one of the main focus areas. But we also have topics on systems, and that's what I will be covering. So talking about building systems, evaluating systems, and then focusing on the systems as an object of study, rather than just a tool to get something done. And that's what I want to focus on in my talk. So it's not deductive, it's mainly empirical. So that's one of the main things. And we very much focus on the performance of applications, performance of systems. So performance of not just one application, but of any application that runs on this particular system that we are measuring. And our goal is to improve performance, to reduce runtime, or also reduce energy consumption on, in particular, large multi-core servers. So that's what I wanted to get out as the context of the work. And that's also looking forward to hopefully having more systems talk in the series of live DSG seminars in order to cover the different areas as well. So assessment will be mainly empirical, looking at performance. We look at a high-level parallel languages. I mean, that's one common ground I think that we have as a group, which is very important. So high-level languages, Haskell in my case, Haskell, or declarative languages in general. The important thing, though, although we use a concrete language as the platform that we embed things in, the techniques that we're talking about are not specific to that particular language. It's not particular to parallel Haskell. As a matter of fact, we take this work that I'm talking about here as a starting point for a proposal that we are just about to wrap up now. And we are studying different languages, Java, Clojure, Scala, on the JVM-based platform, as well as parallel Haskell, which is the topic for today. Okay, so can I get the top row away somehow? Okay, good. Okay, so I started off with the bad practice of having a lot of acronyms in there. So let me get started and explain what's the topic of our study and what is NUMA. So NUMA stands for non-uniform memory access, and it's visualized over here. Can you see that properly? You might take off the light if it's not. Okay. So it's visualized by the picture on the right-hand side. Typically, you think about memory processes as one of the boxes up here. You have a multi-core, many processors, you have memory, all of the memory visible to all of the processors connected to the bus. And if you do C programming, you can address any location in the space, in the address space, and all memory locations are equal. So that's an abstraction, and for the scope of this talk, just forget this abstraction, because that's not how the machine actually operates internally. Of course, there are many other things that we abstract over as well, but the one thing that we want to expose in this work, which is important for the context of NUMA, is modern machines are partitioned into a group of what we call NUMA regions. So each of the block up there, a set of processes and memory, is one NUMA region. It's still all a shared memory machine, so you still have access to all the locations in memory from each of the processors. So you can go from the leftmost processor here to the right memory, that's okay. And you don't need to change anything in the program. You see it's just going to be referenced. But what's happening on the machine is that request will have to go not to the local memory, it will go through an on-chip interconnect to a different memory location. And that can be, in that sense, remote. So the interconnect is a fairly central component. That's one of the key technical aspects to bring down the access time. But still, and that's really the bottom line here, access time to remote regions are much slower than to the local region. So on the small mesh or kind of rangers, so the server style machines that we tested things on, you typically see a factor of 2 to 3 faster access to local as opposed to the remote memory that you have in a distant region. So that's quite substantial. Yeah.
Will you go on to contrast this or compare it also with the role of caches in these architectures?
No.
Or should we see these as completely orthogonal considerations?
It's orthogonal. It's obviously also an important aspect and very important for performance. But we don't bring caches into the picture. That would go one step lower on the abstraction layer.
Okay.
And yes, I mean, in reality, each processor has a cache as well. And that's the same in all the components that we have.
Or many layers.
Several layers of cache. Some shared caches. So I mean, one more realistic picture would be to have the one cache associated with each of the processors, some cache shared between some of the processors. Also very important for memory performance, but not the focus of our study here. We focus on the impact of these regions and access to different memory locations in different memory regions. So 2 to 3 is fairly substantial in terms of access time, also considering that memory access is the most expensive part in computing the program. It's not the operations themselves, so like multiplication operations. But even more so on some of the top-end machines. For example, we have, so I was visiting Rispins last month, so we managed to get access to one of the largest NUMA machines, shared memory NUMA machines, with 1700 cores in total. On this machine, which is really the top range machine in the spectrum, in its GI-based shared memory machine, you can have a difference of up to 14 times faster if you access local as opposed to remote memory. So placement is really important, and that's what we will be talking about in this presentation. It's mainly profiling. Profiling has the programs, how they behave on these architectures, what's the impact of memory, what's the distribution of data across the NUMA regions in these architectures. And the other thing is, yeah, NUMA is becoming mainstream. It's not just a niche market. NUMA has been around for something like 20 years. You can see it probably on your laptop if you check things out. Anything that has a lot of main memory will have NUMA as the architecture. The large machine, the 1700 core machine, by the way, has something like 20 terabytes of main memory. We at Terraquad will be getting a cluster of big servers between half a terabyte as main memory. So certainly these will also be NUMA architecture. So it's very relevant for a particular server level machines. So we want to do profiling in order to manage the memory or observe the performance of the memory. And you can do the profiling on several different layers. And the list here is basically bottom up. So you can profile things on the hardware layer, which is done through typically a coprocessor that you have on pretty much any modern architecture. If you look at an ARM chip or Intel chip, they typically have a coprocessor which does several things. One of that is you can configure registers on the coprocessor to count things like the number of cycles executed in a program or the number of cache misses implemented or hit in the execution of the program. And I've done this in my Raspberry Pi course. It's fun to do, but depending on your interpretation of fun, of course. But it's very obscure. You have very obscure specialized assembler instructions to set and configure one particular coprocessor. So that's probably not the best layer to work on. It's the most precise one. You can do things on the operating system layer. So you have libraries like NUMA Control or NUMA Prof, which give you C libraries which abstract over the different architectures. The hardware level obviously is specific to that particular chip. The assembly instructions would be specific to that chip. That's an abstraction, and that gives you typically C libraries. The level that we work on is mainly the language implementation. And our argument here is you can do the profiling on a lower level, yes, and we actually do that at the first part of the imperative part in the presentation. But when you look into the runtime system, you actually know more about the program that you're executing. The program is not just a black box. You know how memory is laid out. You can profile execution and keep record where things are allocated and give a profile of the application and adjust the behavior to the application profile that you have. So that language implementation layer is the main one that we are focusing on. And you also have explicit languages which can actually define where, in which region to put allocated data. We don't want that. We still want to maintain the abstraction that we have in Haskell or Java or Clojure of just allocating, not tying things to a specific distribution of regions. You can hard code it in a C or C++ program that gives you more performance for that one application, but it's very architecture dependent and obviously also application dependent. So we cover a range of different languages, managed languages like Python, Java. The main one for us is Haskell, and this is basically the software architecture that we are talking about. So for the whole project, we have the range of languages. For the scope of this talk, we have Haskell, parallel Haskell on the top level. We use Gang SMP, so that is our version of the Haskell runtime system, designed to work on a distributed network of machines, but the SMP in there also indicates it can also use shared memory. And we use that combination of distributed design with a shared memory support as well to then run on the operating system, so that's the generic part, and map this down into hardware, which is structured in regions of memory plus set of processors connected through this interconnect here. So the opportunities is, so first of all, we want to observe what's the memory performance of our program. The opportunity is that we can actually adjust the behavior and tune the execution of the program to the behavior of the application. We are not yet at the stage of tuning. So what I will be reporting is mainly observing properties of Haskell programs. So the proposal that we are working on, that is about actually tuning and hopefully get funding for doing the tuning part. We aim at a reduction of runtime. With that, it also comes a reduction of energy and also of carbon emissions. So that's our main direction in the work moving forward. Again, it's still a bit of context, but I want to stress this at the beginning as motivation. We think Haskell is a perfect case study for these kind of memory management use cases. Mainly because Haskell is a very intensive on the memory system. It allocates very heavily, mainly because of the laziness of the language. You have a coroutine aspect of jumping forward between producers and consumers of data structures. And because it's a stateless execution model. And when you compare different or the same program in different languages, typically Haskell has a far high memory footprint, which from our point of view, in this case, it's a good thing. It's a stress test for the memory system, a stress test for the NUMA performance. And we expect that other languages will hit similar problems that we see in Haskell now when we talk about big data application scenarios, which need a lot of main memory as well. I won't talk much about the details of the runtime system. Yeah.
Can you go to the previous slide?
Mm-hmm.
So you talk about immutability, of course, but so you talk about Haskell as a stress, and I agree with that. But I mean, immutability also makes things, for example, easier, right?
Okay. Yeah.
In the sense that the semantics are easier. If you were to do static analysis, it's
Yeah.
easier. And you might lose that when you move to Java or Scala, for example, right? So
in the bigger picture of the toolchain, yes, that's a lot of benefit, and that's a lot of advantages of bringing in statically inferred information. We are not working on these kind of front-end parts of the toolchain of extracting information to feed it in. So what we plan to do in our project, based on the data, is mainly to observe layout of data in the main memory, how things are distributed, and use that information. So the information is profiling based in order to get that information. There is, and I think that's already big enough a chunk of work to focus on, and to would be a second step to take on information about data layout or other statically analyzed data to further optimize the performance.
Okay.
And that could be fed through optimization phases in the compiler with our NUMA AVR.
if you talk about reasons, it seems like reason-based analysis.
Yeah, I mean, that would be a natural link. It's fairly big gap of abstraction there. But yes, I mean, region-based data would be a good way to go. Yeah, James?
What's the relative cost of loads versus stores on NUMA architectures? Because you can see a high allocation rate. Okay, it's me loads of one-time stores, but possibly many loads from them,
No?
rather than a mutable state model where you might be restoring many times. Are they comparable in cost, or is one significantly cheaper than the other?
This the main memory technology nowadays, this SD-RAM, load and stores are roughly the same.
Okay.
The same cost. So the typically models, the cost models that you see, have the same value for both. Now, but that's a very interesting point, and actually also related to the proposal that we are working on. I'm not covering that in the main part of the talk, but another very interesting direction related to memory is also the emergence of NVM, non-volatile memory. And that's not just the technology that you already have in your laptop with SDD cards. So that uses NVM as a replacement for hard disk investment. And it makes what we normally have on a hard disk much faster, which is great. But there's also a new generation of NVM technology coming up, which is called, I think, PCM, phase change memory, which is much faster than the other technology for the SDD cards. And that is designed now as a replacement for main memory. So I think the trajectory there will be that SD-RAM will be either phased out or probably more in the more immediate future will be complemented by NVM memory based on PCM, which is still about 1.5 to 2 times slower than SD-RAM, but it has two main advantages. You can get quite a lot of NVM main memory, so you can give bigger memory blocks, and that's the link with your questions. For that kind of NVM memory, it's actually asymmetric. Stores are much more expensive than load operations for these NVM memories. And there's a quite good body of research in order how to use that in applications. We have one work package that aims of using the profiling that I will hopefully talk here, and then use that also on the concept of NVM memory on the hardware level. That's actually a very exciting development, and there's a lot of research going into that direction. So I think it's quite relevant as well. Okay, yeah. To wrap up context, one of the main issues about GHC runtime system, the parallel runtime system provides a notion of potential parallelism, which will be instantiated at a certain point, but can be discarded. The second important point is based on a generational garbage collector, which is pretty much mainstream. It's standard. I think most modern systems use some form of generational garbage collection. Important notion here is the data in the generation is basically stored by age of the data. So generations map to age of the data, which complements or sometimes also complicates our view. We are interested in distance. So where in the memory is the data located? So there are two orthogonal directions that we're also exploring in this piece of work. The matrix here is one thing I want to put out at the beginning. You can't actually get this matrix if you type NUMA control, I think, -H on your machine, if the package is installed. The matrix here is the kind of matrix that you will see in later parts as well. It has basically the NUMA regions both in the rows and in the columns, and the entries give you the latency, an abstract notion of latency accessing or doing a lookup from one NUMA region to another NUMA region. So which means on the diagonal here, you have the low numbers. So 10 is a kind of abstract unit for the cheapest access that you can get. And that's what you get in the local access from, for example, region 4 to NUMA region 4. You then have a lot of 16, so these are kind of slightly further away in this topology on the chip, which gives you 1.6, a factor of 1.6 more expensive access. And you have 22s here, so that's the highest factor. So the most expensive lookup is a factor of 2.2 to a remote NUMA region. And you can see that actually, if you look at one of the rows, the most common one is the 16. So 50% of the lookups would be in the medium range. There's just one local region, and there are 3 remote regions, which is of relevance for interpreting the data that I'll be looking at. We have 3 benchmarks. I won't go into these in details. It's one symbolic computation, some Euler benchmark, which has, in essence, a map-reduce structure. Well, there are 2 versions. One is a map-reduce, one is a divide and conquer structure. and we have RSA encryption as a compute-intensive program. So the results are structured in 2 stages. And the first stage here is basically using existing tools in order to analyze what's going on. And the second stage will then talk about introducing new profiling information or new ways of looking at the data. So that's our main contribution, these new tools, and analyzing the data for Haskell programs with these new tools. You've probably seen that kind of profile before. It's one of the standard profiles that you get with GHC, a heap profile. You have execution time on the x-axis in seconds. You have the residency on the y-axis. So residency is the amount of heap that's alive at a particular point in the execution of the program. And that's typically the main factor when we talk about heap consumption. That's the main stress on the system. And you can, what you get is also attributing memory to cost centers. Where does the allocation come from? I won't talk about this because I'm not analyzing the programs. I'm talking about the system. But the main picture that you get here for the data parallelism order is you have a big peak in allocation. So this is the data parallel version of some Euler. It creates a fairly large data structure at the beginning, a long list, and different processes then operate on this data structure and gradually work through the data structure. So it's declining in that sense. One thing to keep in mind, the maximum residency is roughly 5 megabytes for the data parallel version. In the divide and conquer version, we have a fairly different picture. So divide and conquer, as you would expect, goes over the data structure, chops it down into half each step, and does the processing. It does more local allocation in total, and it has a fairly steady picture of heap consumption. So it does allocate a fair amount at the beginning, but it is far lower in terms of the total residency. So it's roughly a factor of 5 lower than the data parallel version, and the same drop in the allocation that you see as well. The third one, the RSA encryption algorithm. So that's a more a compute-intensive rather than data-intensive algorithm. That's why we pick it as a contrast point. And that has probably a more common picture. I mean, if you analyze your program, you probably have something like this. You gradually build up heap. More and more heap is allocated in the different cost centers, and you have a peak towards the end of the execution. So that's the picture that you get with the default tools. You get information about heap, mainly heap over time. Residency is the main piece of information when you tune your program. Typically, for us, it's the information about how much heap in total is consumed by these programs. So the next step is still using existing tools, but that now brings that's now what we introduce through our work. In the first step, we use an existing profiler in order to give us information where in the memory the data is actually allocated. The previous picture was kind of the global picture, not splitting it out in NUMA regions. So NUMA Prof is an existing tool that can be used as part of the software layer in order to profile the data. So if you go back to the picture that we had here, you have here the software stack that we are working on. So Haskell runtime system OS. You can think of NUMA Prof as one slice in the layer below the runtime system, using operating system libraries in order to get information about the location on the main memory. And the great thing about this setup is you can use the tool with directly the binary that you've compiled and that runs on your virtual machine in order to monitor execution and to attribute allocations to places in the main memory. The downside is when you do this kind of simulation, well, it's not simulation. If you do this kind of intercepting calls to the operating system to get the information, it's very, very slow. So the measurements, doing the measurements take quite a significant amount of time, but working on this label here has the advantage we don't need to change anything in the application or in the runtime system. So that's a good first step, therefore, in order to analyze what's happening. And so first of all, what is this kind of diagram? It's a heat map. The semantics of the heat map is it tracks lookups from a particular processor in the NUMA region to data in a different or possibly the same region. So when you look up, for example, for 3, it would give you a counter. So the color here is an indicator for the counter of lookups into this particular area. Blue is the lowest color, the lowest value. Purple, which you might see some on the unpin side, is medium, red is high. So it gives you a visual indicator on where the main load is in the execution. And it tracks, for example, how often a processor in region 4 looks up data in region 2 for this particular cell. So that gives us the main information. In this case, we track excess of data as the thing that we are counting. And that's typically the main thing that we're interested in.
So can we take from this then that the main thread is running on a core in region 3, which is producing the data, and all of the others?
That's what I'm coming to, supporting through other profiles. I think you can, with experience, you can guess this kind of behavior already, because you have one hot region here. So you have one region which contains the main data, the most important hot data which is being looked up. And we can validate this hypothesis that it is actually the data from the main thread which is triggering this by doing more profiling with later tools that I'm introducing. So the one thing is we have the hot region, which contains most of the data. The other thing, and you probably can't see that on the screen here. You can see it on the screen here. So you still have a diagonal which is slightly different in color. It's a light purple color rather than a blue color. So there is good locality in terms of local access. It amounts to roughly 28% of the lookups that are local. But the dominant one and the main thing that we see is we have 82% of the lookups of memory are actually made in this hot region. So that's the dominating factor here. And that's for the data parallel Euler version. We have a similar picture for the other programs, for the divide and conquer Euler and for PRSA, for the encryption algorithm. It's again some diagonal with local access, but also a hot region, which is in different regions for different programs. It's also in a different region for different executions of the same program. And we have a hypothesis that this is coming from the main thread that does the allocation. And in the following tools, we aim to validate this hypothesis to validate the hypothesis by developing more tools that give us information about the execution. Before I move on to these modifications to the profiling tools, here a slightly different way of presenting the data, a more abstract way of presenting the data. So this combines the information that we had previously on a full matrix, all regions to all regions, and produces bar charts grouped by the latency into the region that we are doing the lookup. So the leftmost bar is the one with latency of 10. So the numbers here are coming from the matrix that I showed earlier on. So this represents all regions with latency of 10, regions latency of 16, regions with latency of 22. And we count in percentage how much percentage of the lookup is going into a local region, the 10. So we want this to be high. How much of the percentage is going into region with distance 16 or 22, the remote one. And we get these specific numbers out of structuring the data in this way. So one of the things that I mentioned early on is the distribution of latencies. As you can see here, what we would expect in terms of percentage is that lookups in the local region are fairly rare. It's just 1 out of 8 regions would be the local regions. So we would expect, if it's completely randomized, that we have something in the range of 12.5 lookups in the local regions. We have 4 regions being medium and 3 being remote. So we would expect a higher number in the medium regions. But the main number for us is really how much percentage do we see as local lookups in the execution of the program. And the bottom line here is for the data-intensive program, so the 2 versions of some Euler, we have 30% local lookup with a latency of just 10. So that is significantly higher to the 12.5 that we would expect just by looking at the data from the matrix. And it is lower, but just slightly lower at 23% for the compute-intensive benchmark. And this data is a first concrete quantification of the effectiveness of NUMA awareness in the GHC runtime system. So what I haven't said before is GHC, since version 8.2, has a basic notion of NUMA in it. It pings execution context to a region, and allocation is then happening in this particular into this particular region. It's a fairly minor modification in the runtime system, but it gives already a noticeable improvement in terms of runtime, so that you can measure. And the numbers here give evidence for the concrete impact, and that the reduction of runtime is actually coming from the improved NUMA performance that we have. So we want to get a more abstract metric on what is the load on the memory system. So we want to achieve a reduction in runtime in total through better use of the different NUMA regions. And we have statistics as I've shown you before, but how do we compare these numbers between different executions? You could do histograms or bar charts. These are not very good for direct comparison. So what we do in our paper is we introduce the notion of a NUMA access rate. And the idea of the NUMA access rate is just very simple. We take the number of accesses, so the counts in AI, into a particular region. I ranges over the regions, so 0 to 8 in our case here. And we do a sum of these accesses weighted by the latency of the NUMA region that we are accessing into. So it gives us a weighted sum. We divide this by the runtime to have the access rate, which is an abstract notion of how expensive is it to access the data in a given unit of time in this particular program. So if we use that notion of a NUMA access rate, we can calculate the concrete values. For the data parallel sum Euler, we get the higher of the 2 numbers. So as expected, data parallel sum Euler is the most stressful of the 2 sum Euler versions, with 166 billion accesses, or gigs in total. The divide and conquer sum Euler version is less stressful on the memory system. It has a lower value, just half of the memory access rate compared to the data parallel version. In the data parallel version, this is coming from the list creation that we do at the beginning of the program. Remember the heap profile that we had at the beginning? We had the big peak in heap at the beginning of the execution of the data parallel sum Euler. So that does all the list allocation at the beginning, and then reduces it from there. The comparison is the PRSA algorithm. So that actually has a very high load. It's compute intensive. It is less intensive in terms of the total memory that is produced or accessed, but it has the highest load because the access costs for the remote regions are much higher. So the weight in terms of factor 2.2 kicks in this particular picture and makes it the highest load in terms of NUMA access rate that we observe for these 3 programs overall. So that's one step in order to get a more widely usable access metric. And the last part that I want to talk about is a second extension. We have extended in the first extension. Just let me regroup. So in this extension, we extend the NUMA prof tool. So we are still at the point of using an external tool to monitor what's happening in the execution of the program. But we now monitor the NUMA prof tool with an allocation tracker. What we've seen so far is information about data access in the different NUMA regions. What we now want to get is information where is data allocated in the first place. And that's a contribution to the tool. So the implementation is publicly available as an open source tool and modifies the NUMA prof tools that we started working with. And the picture that we get from one of the applications, again, some Euler, is fairly distinctive. So again, the same kind of matrix, but now we are actually counting allocations. So allocations from a processor into a particular NUMA region. And the good picture that we get, as usual, the diagonal is typically a good thing. Now it's not access time, it's allocations. And what the diagonal, the red diagonal shows is actually that the NUMA awareness policy in GHC is working. So when you have a processor that picks up work and starts executing the piece of work as a spark, it will run the program pinned on the particular NUMA region. So that's the NUMA extensions. So the thread that is created will make sure that all new allocations are always made to the local NUMA region that you're executing in. The idea is to keep the data together. I mean, the tension is about load balance, but the main goal is to keep the local data in the local region to have cheap access time. So the red diagonal shows that the NUMA awareness policy that is in GHC is working, and it's almost 100% of the allocation. Yeah.
I can imagine that working for divide and conquer, where you produce more children that generate their own more parts of the some order list.
Mm-hmm.
But for the data parallel version, where you perform a map over that initial list, is it not the main thread which is the only producer of the initial list?
Mm-hmm. Yeah. And again, you probably can't see very well on the screen here, but if you look at the picture, this is not the only red area. So this is the red area of the workers doing their work and generating local data. The main thread is a bit different. The main thread is not one of the pin threads. It's not one of these 8 regions. But the main thread is always, it's not tied to a particular region. It is initially allocated a region in the execution. And all the allocations of the main thread show up in this additional color, which is not one of the NUMA regions. And in this case, the main thread is allocated into NUMA region 3. And that is actually the initial data, the input data that is generated by the main thread. And actually identifying that the main thread allocates into region 3 is a very important observation, because the first one was basically just a sanity check. Yes, NUMA awareness in GHC works. The second part of the picture that we just pointed out links up the 2 pictures, the allocation picture and the access picture. The allocation picture tells us the main thread is allocating into region 3. The access picture shows up whatever is the hot area, the hot data in the program execution. The most access data is in region 3. So this counts accesses, and we see processors from all over the machine access a lot of data from NUMA region 3. And this is exactly the same region that the main thread initially allocates into. So this gives evidence, or well, I would say this is a strong indicator that the behavior that we see here is access to the initial data allocated by the main thread, which becomes the bottleneck and the most expensive part of looking up data in the heap of the entire NUMA machine. So this links the 2 pictures together and allows us to explain what's happening in the execution of the program for, in this case, data parallel some Euler, but we have the same pattern of pictures, just with different regions. So as I said, the main thread is randomly allocated a region, so this column moves around, But in each case, the hot column here matches the column that the main thread allocates into. Okay, so that was one modification that we did, a modification of the generic profiler that we use in order to collect the data. The second extension that I want to talk about shortly in the few 5 to 10 minutes at the end. These are now extensions that Rory made in his project, modifications to the GHC runtime system. Because we don't just want to use a black box execution of the program, we also want to collect more information, what's happening internally in the execution of the program, knowing about how garbage collection runs in GHC. And garbage collection counters are already available. When you run a Haskell program at the end with -s standard error, you get counters like how many garbage collections, how many first, second generation garbage collections. That's important for us. How much time was spent in garbage collection. And what we want to do in the first extension is to get these statistics, not just globally, but split by each of the memory regions. So how much garbage collections did we have in region 1, 2, 3, up to 8, in order to give us a more precise pictures. It's changes in the runtime system is mainly instrumenting the code in the runtime system to get information about regions. We don't change behavior. So that's not yet part of the topic we are talking about. This is a summary of the per region garbage collection counts that we see for the 3 programs in the 3 columns. And what we have in one in this column here, this represents the different generations. We just use 2 generations as the default setting when running the programs. And we count the number of garbage collections in each of the regions, in each of the generations, in the 2 lines, but also in each of the regions in the 8 columns that we have over the entire range here. And I plotted also or wrote down which region is the hottest based on the pictures that we had in the previous profiling exercise. So summaries from this one. We have more first generation garbage collection in the divide and conquer algorithm. So that represents that in divide and conquer, you do generate more local data which is used for a short time period and is then thrown away, till common picture. And it actually shows up that there are more, in total, more accesses to the data compared to the data parallel version. So it's more intensive in the short-lived data. So one way to look at the picture here is that the columns 1 and 2 give you a notion of age. So this line, the 1 line, would represent the young objects that you have. The generation 2 represents the old objects that you have. And we compare this with where in the system are these objects, always referring to number of garbage collections in the sense of how intensive is it to manage these particular directions. So we have mostly young objects in DNC. We have more older objects in data parallel. So we have 49 generation 2 collections compared to just 18 in divide and conquer. That matches the picture that I mentioned earlier. Data parallel, the data parallel version generates the entire data structure at the beginning and keeps this until the end of the execution. So it's a long-lived data structure which corresponds to more garbage collections needed in the second generation. Whereas in divide and conquer, you have fewer long-lived data structures, you have local data structures, local to the execution of the program. And PRSA is mainly compute intensive, not memory intensive. It has in total fewer garbage collections overall compared to the other 2 programs. In terms of region, it's a mixed picture. And on that part, we don't really have strong conclusions, I'm afraid. What we see is it's mainly evenly distributed between the regions in most of the cases. There's one hotspot in PRSA, which has far more garbage collections in the first region. That might be just the region that picked up the first thread, the first of the worker thread. I mean, that's one possible explanation, because typically, so In the runtime system, idle processes look for available work, and in turn, they pick up the work from the pool. The region 0 is most likely the one to pick up the first available thread that is then turned into, first available spark, which is then turned into a thread. But we don't really have strong results on the region or on the column side of things. But the data is available, and that's one of the new things that you get with our tools. And the last extension is again in extension to the runtime system, to the garbage collector, again about profiling. And what Rory has done there is to record GC thread locality. So you get pictures that look like the previous pictures. The interpretation here is now we don't look at the mutation phase, so the actual execution of the program and access or allocation. We look at the garbage collection phase. So we're only interested in the garbage collection phase. And the picture shows us if a thread is running, a garbage collection thread is running in region 5, for example, how often does the garbage collection thread access data in other regions? That's the point where we get information about the distribution of data overall. And we see, so again, blue low values, red high values, gray is 0 values. That is in some sense a good picture. So having 0 values here means that the data that is needed by something rooted in region 5 is spread over 4 regions. But it's not spread all over the meshing. So there's some notion of locality. I mean, ideally, you would want it to be in the same region as the process itself, but you never get the perfect picture. So there is some notion of locality in both generation 1 and 2. The difference of the pictures is this is generation 1. So these are the young objects which have more locality. You also have some older objects, that's generation 2. You have less locality there. Mainly that's the big data structures that are often allocated at the beginning. Again, I think that's data parallelism or Euler. So you have a wider spread in terms of counters. And that's looking forward for us the starting point to actually look into modifications. How can we modify the behavior of the runtime system? What we would like to get is a picture where things are more local after the garbage collection. The data in this region, for example, might be moved into the local region here, trying to get the data that is needed by a processor to the region where the processor is actually living. And that's the main direction for the proposals that we are currently working on, exploring this for Haskell and for Java. Yeah.
So you said that one was better, but actually the numbers suggest if the right one is generation 2, then it's actually better than the second one.
Yeah, so if you count, I think that's mainly the first part here, which comes into the picture. I mean, this one is better because you don't have 0 access to some of the areas. So it's good not to touch some of the regions at all in order to have a more local picture. You have more separation here, but I'm not sure what the exact numbers are in the different regions.
Well, I can imagine if you add up, let's say, the diagonal, then it's better in generation 2 because the big red one is on that one is on the wrong. Is one accessing 0 is a huge chunk.
Yeah. I mean, that is, I think it fits more perfect than this one. These are always normalized numbers in terms of how much of the percentage of the counts is in a particular area. The one thing that you don't get out of the picture is also the absolute numbers in terms of what are the accesses to the different picture. But yeah, I think the biggest influence would be the purplish diagonal that you have in the generation 2. That's the good picture that you want. That's not the good picture, but that's the one that we get from the early allocation. So you can get the pictures and you can get concrete numbers out of these instrumentations of the runtime system. And the other thing, additionally to generation 1 and 2, you also have the area of static objects. So that are top-level objects, top-level constants, big data structures, list of, for example, a list of all prime numbers that you might have on the top level. And the difference there is quite pronounced. So for the caps, So the static objects, top level constants, we don't see any locality here. So we have, well, probably not a lot. I mean, in terms of absolute counts, these are very low. But what we see here, they are concentrated in just two regions for some reason, nothing in other regions. So there's no locality really with static objects at all. And depending on the application, that might be also an important issue, accessing these tabs. And again, one way forward would be to look into ways of different or modifying the garbage collector to move data in these static regions around, again, local to the processor that needs the data, information that we can track during garbage collection time. It will add overhead, but it will give us an opportunity to move things around and be more efficient in terms of memory access. Okay, so that's basically the empirical part of the work that I wanted to cover. So, and to summarize, so well, I think one takeaway message in itself would be NUMA is the predominant memory architecture that's around nowadays. And it means that there are significant differences in access time. 2 to 3 is a standard factor. It can be much higher. And that's an architecture that will stay in particular on servers. We have observed a couple of numbers with existing tools, and we managed to do a quantification of the effectiveness of GHC's built-in NUMA awareness. So GHC already does simple things in pinning a thread to the context that the process is working in, and keeping the data local to this particular thread, allocating just in this one thread. This is effective because we get local accesses, 30%, 23%, which are quite a bit higher than the notional 12.5% that you would expect in a random distribution. That's the case for each of the benchmarks that we have seen. We've introduced a NUMA access rate or proposed NUMA access rate as a metric to compare different programs. It's as a metric, you use it for comparisons in terms of what is a better program, what is a worse program, which might give you also a handle to assess the NUMA efficiency of your particular application. We mainly look at it as doing things in the runtime system. It might also be useful to expose this to the user in order to get information. Although, yeah, depends on the user whether that's can be used for tuning the program. And we have extended NUMA Prof. We extended the tool, which is a kind of black box tool that can run a binary as it stands and track allocations and accesses. We see with the modification that 100% of the allocations of the Spark threads are local. That's what we expect. Again, it's a sanity check, nothing particularly new, but again, it gives evidence that the existing NUMA awareness is working. And we can, with this tool, also identify as the main thread allocation being the main source of the hot region that we have in this map. So we can identify the reason for the kind of bad behavior in terms of memory access or costly memory access. We don't have strong results from the per generation information, but it's information which is there, and I think will be very useful moving forward in investigating things garbage collection techniques in order to improve performance of NUMA architectures. We draw on several papers in the Java JVM community. I think we can adapt this technique for the Haskell runtime system in order to be efficient in that context as well. And that's mainly the future work that I wanted to cover. So we are moving on to use this information in concrete modifications for these different platforms. But the tools are already there, and that's one of our main contributions in this work. Okay, so thanks for the attention. Also, any questions?
Can you already measure in your pictures the difference between having a small data structure that is used a lot, maybe by many different other regions, and a huge data structure that is kind of used more sparsely? Would that be visible in some way in the pictures you generate, or don't you, if the total sum of accesses would be the same?
So we do have the number of accesses into the region, from the tool.
Yeah.
We do have information, but in principle, we have information about the data structures, how things are connected, looking at the last part, so the GC thread locality. And kind of the picture that I've shown here shows on some abstract level how things are distributed over the region. But we don't have a way to clearly identify, like the cost center in the heat profile, we don't have a clear way of identifying this access comes from this data structure. So there's a kind of a conceptual and abstraction gap there. What does the access relate to in terms of data structure that we have on the program level? I think that would be a gap to be bridged if we want to use these kind of pictures as user level information about
But even so,
particular small
you
data
should talk
structure.
about caps, for example, that don't have locality.
Mhm.
But if the caps are small, you could also duplicate them in
Yeah.
the other regions, right?
I mean,
That would be a reasonable thing to do as long as they're small. And
That
that's
would
why I
be-
wondered.
that would be one option to actually duplicate. I mean, in the Para context, we considered duplicating work that might be in some sense actually better to do things independently. You might also think about duplicating data in order to improve locality. I mean, I should say the caps, they come up very prominently in the pictures, but the total numbers are not so high. So you would need to actually look how much impact do the caps have on the NUMA access rate to see whether that's worth doing. But that's definitely directions to look into in order to improve the behavior or to learn more about the structure of the execution. So for us, that's really the starting point in that direction. Okay. So, yeah.
So the introduction of NUMA-aware allocation in 8.2 GHC, is the idea there that a thread can consume more quickly objects that it's produced rather than something more sophisticated, which is producing objects that nearby threads have produced within the same NUMA region?
I think it's just about the own thread rather than nearby thread.
Right.
It's a very simple modification, and it basically just pins the allocation for that thread to the region the thread is working in as the immediate piece of information.
Right.
I don't think there's any notion about other threads on the same NUMA region to keep neighbor that data or less related data on the same processor.
So it's just allowing a thread to consume its own data as quickly as possible.
That's the main idea. So I mean, in some sense, the NUMA awareness it's picking up the low-hanging fruits that are out there and the things that you can achieve in the runtime system without a lot of restructuring. It's not a big exercise and nowhere near the kind of stop the world versus concurrent gauge collection, which is a huge refactoring. It's isolated changes that need to happen in the runtime system for that. And but it does work as the numbers show.
With a question in the chat.
So any questions from online participants?
So whilst they come in, which is faster, the divide and conquer or data parallel on this NUMA architecture?
I think the data parallel one is the fast one.
I thought the big contender was going to say that actually, if you want to program NUMA architecture, you need to program in a divide and conquer style so that you can have producers.
I don't have that on the slides. I would need to look it up, but I think data parallel was the faster one. Yeah. I mean, there are obviously a lot of factors coming together about how you structure the algorithm. Yeah.
So there's a bit maybe on topic, but you mentioned at the beginning that this is in a way related to the non-volatile memory. I know of some research that's looking at semantics of non-volatile memory and what does that mean.
Mm-hmm.
Are there some complementary questions that are related to semantics? Is something novel happening here, or can we just, for the purposes of some kind of verification of this, simply say we're just not things like normal memory? Or are there some interesting theoretical things that can be also work?
Well, I think one of the main properties is the asymmetry in load and store operations that we mentioned already, because that makes quite a difference. I mean, here we don't need to expose well, we do expose allocations versus access, but we don't count or try to balance the numbers. So I think that the link there with NVM would be to use the information about locality that we do expose in our tools, and to keep things together in that context and decide which part of the execution to do on SDRAM, for example, which has different characteristics, and which part to do on an NVRAM or an NVM run. And one way to go in that direction would be to look at the big constants, so those that are rarely changed, maybe generation 2, move generation 2 to the NVM, which is garbage collected less often. Keep the generation 1 into SDRAM, which has the symmetric behavior and is accessed far more frequently. It's still fast, SDRAM is still faster than NVRAM. So that are aspects that come into the picture looking at costs or dynamic aspects of the NVRAM. I'm sure there's quite a lot of work also in terms of feeding more information to the program, for example, to better use the different memories. So it is quite a big area. We are focusing mainly on the garbage collection here and how to structure things at runtime. But it's also a big area in terms of how you program the NVRAM, because when you think about the NVRAM as replacement for SDRAM, you think about accessing to pointer in the usual memory interface. You could also program it as a file system and like memory map file systems and programming it in a different way. And I think a lot of the momentum in the supercomputing community with NVRAM is to actually use the persistence of the NVRAM in order to program the applications in a different way. So to not have to encode movement to hard disk and into memory in your application, but just use one big block of the NVRAM, and then you can actually manage it more flexibly. So it kind of breaks down the barrier of what's a file, what's main memory, and these are very different things that you need to treat quite differently. But that's mainly in the direction of persistence for the NVRAM. We are here interested in the larger volume and the different access costs that we have in NVRAM compared to SDRAM.
I have another question. So, I mean, the Haskell difference between, or let's say the distance between the program on the one hand and what it actually in the end maps down to is quite large. Right? That's why we program this level, because there's so high level of clarity. And this is still pretty much at a high level kind of information. I mean, you're not even thinking about providing that information to the programmer, I think, and at the first instance. However, the programmer can already influence substantially the behavior at runtime of Haskell programs by having strict annotations, things like that, right?
Yep.
So I can imagine the programmer kind of sees that his program is not performing, and then he goes all this way to kind of improve by putting strict annotations everywhere. How does that connect to basically the kinds of things that may happen some levels underneath? Maybe countering whatever annotations he has placed or enforcement. Is that something that you'd like to look at, or?
Yeah, I think it's certainly a very big gap to bridge in terms of the levels of abstraction. And I think what you would need is something like cost centers to identify where the data structures are coming from in order to link things onto the user level, to link it to sources in the program, rather than just having counters for the different regions. I mean, we still view these tools mainly as tools for compiler writers, for developers for runtime systems, in order to kind of make generic decisions that should work well for all programs, rather than tools to be used by the application programmer. So on the application programmer side, you have some intuition with strictness kind of being one important factor, and modifying this, putting in annotations. or analyses working on that level in order to modify the performance. So we don't view this kind of NUMA awareness as something that would pop up on the application programmer level. But if you want to promote it that high up, and still also for compiler writers, I think some cost center style attribution of costs to things that are logical units in the program rather than hardware specific units. I think that's the main bridge to, or the main gap to bridge.
Right. Okay. If you have any more questions, maybe we can continue in the couple of minutes. So let's thank you again.
Okay, yeah. Thank you very much.
So thank you for the online participants. Yeah. Well, good luck with that. Yeah, really happy about it.